Hello students, welcome to this video presentation on heat transfer and Newton's law of cooling, which is given as part 3 of thermal properties of matter. Heat transfer is a very descriptive chapter and explains the modes of transmission of heat, that is conduction, convection and radiation. In this section, we have also explained black body radiation with statements of Wien's displacement law and Stephen Boltzmann law. The greenhouse effect is also explained in section 11.9. And further, Newton's law of cooling, which explains the phenomena of rate of loss of heat and its relationship with difference of temperature. Finally, we will end this video by answering questions of 1 and 2 marks as well as some word example. Please listen to my lecture very attentively and note down all the important points, as the same will help you in your examinations. I welcome you once again. Heat transfer. The transfer of heat from one body to another may take place by any one of the following modes. Conduction. In conduction, heat flows from hot end to cold end. Particles of the medium simply oscillate but do not leave their place. Please see conduction. Here a metallic rod is held over a heat source, and the transfer of heat takes by actual physical movement, that is passing through the rod. Convection, each particle absorbing heat is mobile. Here, the particle itself in the atmosphere absorbs heat and it moves physically, and heat is transferred. In radiation, heat flows without any intervening medium in the form of electromagnetic waves. Please see the diagram on the right hand side. All the three modes have been explained. Here, the radiation waves are moving and in the medium without any intervening medium, and it is felt by our human body. So in conduction, medium is necessary for conduction. In convection, medium is necessary for convection, and in radiation, medium is not necessary for radiation. Conduction is a slow process. Convection is also a slow process, whereas radiation is a very fast process. In conduction, path of heat wave flow may be zigzag. It can be zigzag or straight through the conductor. In convection, path may be zigzag or curved, whereas in radiation, path is a straight line. That is, the waves travel in the straight line. Conduction takes place in solids. You see, there is a rod through which the conduction is taking place. Convection takes place in the fluid. Convection flows through the fluid, whereas radiation takes place in gaseous and transparent media. In conduction, the temperature of the medium increases through which heat flows. And in convection, in this process also, temperature of the medium increases. In case of radiation, there is no change in the temperature of the medium. All these phenomena are modes of heat transfer. Conduction and convection and radiation are explained in the subsequent slides. Please listen attentively. Heat transfer, conduction. We will study about conduction in detail. Conduction is the mechanism of heat transfer between two adjacent parts of a body because of their temperature difference. Here, heat transfer takes place by conduction from hot end of the rod through its different parts to the other end. Gases are poor thermal conductors, while liquids have conductivities intermediate between solids and gases. Heat conduction may be described quantitatively as time rate of heat flow in material for a given temperature difference. The figure shows the steady state of heat flow by conduction in a bar with its two ends maintained at temperature Tc and Td. See, this is a bar through which conduction takes place, and here this end is maintained at temperature Tc, and this end, the other end, is placed at the temperature Td. So here Tc is greater than Td, that is temperature of C at the end C is more than the temperature at T, that is Td is cooler. It is found experimentally that in steady state the rate of flow of heat or heat current. So rate of flow of heat is nothing but heat current. H is proportional to the temperature difference, that is Tc minus Td. And Tc is the temperature here, this end, and Td is the temperature at this right hand side end. So the temperature difference is Tc minus Td, and rate of flow of heat is proportional to the temperature difference Tc minus Td. Note down this point. Hence, H is proportional to the area of the is also proportional to the area of the cross section A. So this is the cross sectional area of the rod here. So heat is proportional to temperature difference. He is proportional to area of the cross section. Therefore, heat is also inversely proportional to L length. That is, H is proportional to 1 by L. So summing up and removing the proportion and substituting removing the sign of proportionality, we get H is equal to K into A into Tc minus Td over L. Here K is a constant. The constant of proportionality K is called the thermal conductivity of the material. The greater the value of K for a material, the more rapidly it will conduct heat. So the constant of proportionality, that is thermal conductivity, is more. The heat will be transmitted very fast, and conductivity will be more. The SI unit of thermal conductivity K is expressed as joules per second per meter per Kelvin, or it is also written as watts per meter per Kelvin. This you note down, SI unit. And in the table, please see the table given in table number 2, the thermal conductivity of some of the materials. In column 1, a list of metals is given like silver, copper, aluminum, brass, steel, lead and mercury. And its thermal conductivity is expressed in joules per second per meter per Kelvin is given. So if you see the figure, silver amongst all the metals, silver has got a very good thermal conductivity of 406. Next is copper. So silver, copper and aluminum are very good conductors of heat, whereas brass, steel are relatively less. As compared to metals, there are non-metals are listed in column number 3. Non-metals are insulating brick, concrete, body fat, felt, glass, ice, glass wool, wood and water are given, and their thermal conductivities are given in joules per second per meter per Kelvin. You can see these are all fractions. That is, an insulating brick has a thermal conductivity of 0.15 as compared to thermal conductivity of silver, which is 406. Please note the silver's difference, the difference between a metal and non-metal. Similarly, a list of three gases like air, argon and hydrogen are given here in the column number 5 and their thermal conductivity in terms of joules per second per meter per Kelvin is also listed. So air has got a thermal conductivity of 0.04. You see the fraction and decimal place after decimal 0.4. Similarly, argon has a thermal conductivity of 0.016 and hydrogen has comparatively 0.14. Please note down and this table and just note down the difference between metals, non-metals and gases and their thermal conductivity. Now we will take up an worked example to understand the phenomena of heat transfer. Question number 6. What is the temperature of steel copper junction in the steady state of the system shown in figure below? The figure shows a furnace which is kept at 300 degrees Celsius connected to a steel rod and the steel rod and a copper as shown in the diagram, and it is bound by an insulating material so that the entire heat passes through this metal or combination of steel and copper, and there is the other end is ice box which is at 0 degrees Celsius. I will continue reading the problem. Length of the steel rod is 15 centimeters. Length of copper rod is 10 centimeters. So the temperature of the furnace is 300 degrees Celsius. Temperature at the other end is 0 degrees Celsius. The area of cross section of the steel rod is twice that of the copper. So steel rod is twice that of copper. So copper rod is thinner and steel rod is thicker. That is, its area is twice that of copper. Thermal conductivity of steel is given as 50.2 joules per second per meter per Kelvin and copper is 385 joules per second per meter per Kelvin. This is also given in the previous table. So let us solve it. Answer. In the steady state, rate of heat flowing across a cross section of the rod is same at every point along the length of the combined steel copper. So that means in steady state, the rate of flow through the cross section of this rod, steel rod as well as copper rod is same. Let T be the temperature of the steel dash copper junction. So this is the steel copper junction in the steady state. Then therefore thermal conductivity of steel into area of cross section of steel into the temperature difference 300 minus T divided by length of steel rod should be equal to thermal conductivity of copper into AC, that is area of cross section of copper into T minus 0 divided by LC. We are required to find the temperature temperature of the combination at the junction. Therefore, substituting the values, it is also given AS is equal to twice the copper. Area of cross section of steel equals, this is given, and length is 115. So these are all given quantities in the question. You please write down as given and note down these values. Pause it and note down. So substituting the values for Ks and various parameters in this equation 1, we get T we have to determine in both, which is an unknown in left term as well as the numerator in the left term as well as the numerator in the right hand side. So simplifying, for T we get the value of T as T is equal to 44.4 degree Celsius. Now we will take up convection. Convection is a mode of heat transfer by actual motion of matter. It is possible only in fluids. Convection can be natural or forced. There are two types of convection, natural or forced. The figure on the screen shows the convection cycles, that is land to sea, land to sea and sea to land, that is day as well as night. So natural convection. In natural convection, gravity plays an important part. When the fluid is heated from below, hot parts expand and therefore becomes less dense. That is, they become lighter as compared to the lower part. Because of buoyancy, it rises. The hot fluid flows up and the upper cold part replaces it. That means cold part goes down and hot part goes up. This again gets heated and rises up and is replaced by relatively cold part. This process goes on. Natural convection is responsible for many phenomena. So this happens in case of convection cycles, that is between land and sea breeze, as shown on in the diagram. Similarly, rain winds like monsoons, trade winds also are due to convection. The second type of convection is forced convection. In forced convection, material is forced to move by a pump or by some other physical means. The common example of forced convection systems are forced air heating system in home, that is AC. The human circulatory system in our body is also a form of forced convection, and the cooling system of automobile engine. So when we know through radiator we cool and circulate the hot air and all that. That is also a form of forced convection. In the human body, heart acts as a pump that circulates blood through different parts of the body, transferring the heat by forced convection and maintaining it at a uniform temperature. Natural convection takes place from bottom to top, while forced convection takes place in any direction because of we are using the work done by a pump. Natural convection is not possible in gravity-free region such as free-falling lift or an orbiting satellite. Now we will take the third mode of heat transfer. It is radiation. Radiation is a process in which heat is transferred from one place to the other without intervening medium called radiation. The process, I will read once again for you, the process in which heat is transferred from one place to other without intervening medium, that is without a medium in between, is called the radiation. Now we will study about the properties of thermal radiation. Thermal radiations are also called infrared radiations. Medium is not required for propagation of radiations. Everybody whose temperature is above 0 Kelvin emits thermal radiation. So everybody, including our human body, also emits thermal radiation because its temperature is above 0 Kelvin. The speed of this radiation is equal to that of light. They follow the laws of reflection, refraction, and interference, diffraction, and polarization. Please note, the important characteristics of radiation are they follow the laws of reflection, refraction, interference, diffraction and polarization. Now we define a term called radiant energy. All bodies at all temperatures and at all times radiate energy in the form of electromagnetic waves called radiant energy. As we have seen, the radiation takes place in the form of electromagnetic waves, and the energy radiated by the bodies is called radiant energy. In an electromagnetic wave, electric and magnetic fields oscillate in space and time like any wave. Electromagnetic waves can have different wavelengths and can travel in vacuum with the same speed, namely the speed of light. So, radiation can take place even in vacuum. And electromagnetic waves have different wavelengths and it travels in the vacuum. That is, it travels at the speed of light. That is, the value of speed of light is 3 into 10 to the power of 8 meters per second. You will study more about electromagnetic wave propagation in class 12. Till then, just remember that electromagnetic waves, that radiation takes place in the form of electromagnetic waves which has different wavelengths and it travels in vacuum also. The emission rate of radiation is faster at higher temperature. So, if the body is at higher temperature, the emission rate is high. Thermal radiation. The electromagnetic radiation emitted by a body by virtue of its temperature, like radiation by a red hot iron or a light from a filament lamp, is called thermal radiation. That means a red hot iron rod which is heated to a red hot position or a filament of lamp also emit radiation, thermal radiation. When the thermal radiation falls on the other bodies, it is partly reflected and partly absorbed. The amount of heat that a body can absorb by a radiation depends on the color of the body. That means the absorption characteristics of a body depends on its color. And it is also seen that the black bodies absorb more heat, thermal energy, and they emit radiant energy. So they absorb as well as emit radiant energy better than the bodies of other colors or lighter colors. This is also an important point. Black body radiation. First we will understand what is a black body. As you know, the thermal radiation at any temperature is a continuous spectrum from small to long waves. That means the electromagnetic wave of heat comprises of wavelengths, smaller wavelengths as well as longer wavelengths. When such a wave is incident on a body, on a perfectly black body, the body absorbs all the radiations completely. That is, all the wavelengths incident on it. To understand the nature of black body radiation, we have to conduct a small experiment wherein we heat a body at a constant temperature, say T1, as shown in the curve on the screen, right hand side of the screen. Say we keep the temperature constant at T1 and vary the wavelength. The wavelength is plotted on the x-axis and energy is measured. It is observed in the experiment that as we increase the wavelength, the energy increases. That is, the observations are summarized below. Energy is not uniformly distributed in the radiation spectrum of black body. This curve is also called the radiation spectrum. At a given temperature, say T1, the intensity of radiation increase in the wavelength. That is, if you increase the wavelength, the energy increases and reaches a maximum at a point lambda 1. It can also be represented as lambda 1m. That is lambda m, and becomes maximum at a particular wavelength, and further increase in wavelength. If you further increase it, the wavelength, it decreases, the intensity falls down or decreases. Similar experiments are conducted at other temperatures T2 and T3, where T3 is greater than T2 and greater than T1, and the same experiment is repeated and its plots are as shown on the curve, energy wavelength curve as shown in the figure. Increase in temperature causes the decrease in wavelength. So, as you know, as I said earlier, T3 is higher than T2 and T2, whereas its maximum wavelength is lambda 3, which is less than lambda 2 and which is in turn less than lambda 1. So, T3 is greater than T2 and greater than T1, but lambda 3 is less than lambda 2, which is less than lambda 1. Hence, increase in temperature causes decrease in lambda m. Now we will define Wien's displacement law. According to this law, the product of lambda m, that is the maximum wavelength, into T, capital T, is constant. Let it be equation 1. Here lambda m is the wavelength corresponding to maximum intensity of radiation. Say for this curve, lambda 1 is the lambda m for the curve T1. It is the wavelength corresponding to maximum, so intensity is maximum here. Intensity or energy are used interchangeably. Capital T is the temperature in Kelvin. In this equation, capital T is the temperature in Kelvin. The value of Wien's constant is 2.9 into 10 to the power of minus 3 meters Kelvin. So lambda m is in meters and T is in Kelvin. Hence its unit is meters Kelvin. This law explains as to why the color of piece of iron heated in a hot flame first becomes red and then reddish yellow and then finally white hot. So at temperature, say for example, it can be red hot. At the temperature T2, it becomes reddish yellow, and finally it may be white hot at temperature T. Hence, because of variation in lambda 1, lambda 2 and lambda 3, the color changes. Wien's law is also useful in estimating the surface temperatures of the celestial bodies like moon, sun and others. That means if we know, if we can measure the wavelength of the radiations from celestial bodies, we can calculate the temperature T. Light from the moon is found to have maximum intensity near 14 micrometer. If we put the value of lambda m as 14 micrometer, we can find the temperature of the moon, which is found to be 200 Kelvin. Similarly, in the case of sun or solar radiation, lambda m is found to be 4753 Armstrong. if we put the value of lambda m as 4753 in this equation and take this constant 2.9 into 10 to the power of minus 3 meters Kelvin, the temperature of the sun is found to be 6060. The black body radiation can be explained theoretically by Stephen Boltzmann law. This law states that the radiant energy emitted by a perfectly black body per unit area per second, that is, the emissive power of black body is directly proportional to the fourth power of its absolute temperature. If we represent radiant energy as capital H and absolute temperature as capital T, then according to this law, H is directly proportional to T to the power of 4. It is also proportional to the area of the body and its surrounding. Hence, the proportionality sign can be eliminated by writing this equation as H is equal to A into sigma into T to the power of 4. That is, H equals A into sigma into T to the power of 4, where A is the area, sigma is the Stephen Boltzmann constant, and T is the temperature in Kelvin. And its value is given by Stephen Boltzmann, and its value is 5.67 into 10 to the power of minus 8 watts per meter square per Kelvin to the power of 4. Please, this value can be very easily remembered as it is 5.67 in sequence, 567 into 10 to the power of 8. So it is 567 and minus 8. So you can remember it easily. Now we know all bodies are not perfectly black. For any other body, we add another constant E called emissivity of the body and write the equation as H is equal to A into E into sigma into T to the power of 4. That is, E is equal to the value of E equals 1 for a perfect black body or perfect radiator, and it is about 0.4 for tungsten. Example, a tungsten lamp at a temperature of 3000 Kelvin and a surface area of 0.3 centimeter square radiates at the rate of H is equal to, we can calculate the energy radiated by a tungsten lamp as H is equal to 0.3, that is the area, into converting centimeter square into meter square, 0.3 into 10 to the power of minus 4 into 5.67 into 10 to the power of minus 8, that is sigma into 3000 to the power of 4. So its value becomes 60 watt. E is a dimensionless quantity. If Q is the total energy radiated by the body, then Q is given by the relation Q is equal to A into T, that is time into E into sigma T to the power of 4. This is another form of Stephen Boltzmann constant expressing the total energy. If a body at temperature T is surrounded by a body at temperature T0, that is, if we are considering the temperature of the surrounding, then there is a temperature difference of T minus T0. Then H is given by H is equal to E into sigma into T to the power of 4 minus T0 to the power of 4. This is yet another form of Stephen Boltzmann's law considering the surrounding temperature. Now we can use Stephen Boltzmann's law to calculate the heat radiated by human body. Let the surface area of person be 1.9 meters square and room temperature be 22 degrees. So body temperature be 37 degrees Celsius and skin temperature is 28 degrees Celsius. The emissivity of the skin is 0.97 for electromagnetic radiation. This we have to take from the tables. Therefore, H is given by H is equal to 5.67 into 10 to the power of minus 8 into 1.9 into 0.97 into 273 plus 28, where 28 is the skin temperature to the power of 4 minus 273 plus 22. 22 is the room temperature, that is surrounding temperature. That is the 66.4 watts. This is more than half of the energy production of the body at rest. To prevent this heat loss effectively, that is better than ordinary clothing, modern Arctic clothing has an additional thin, shiny metallic layer next to the skin which reflects the body radiation. Now we will study about the very important subsection greenhouse effect. As you know, the Earth's surface is a source of thermal radiation as it absorbs energy received from the sun. That is, Earth absorbs energy received from the sun. The wavelength of the radiation lies in the long wavelength infrared region, but a large portion of the radiation is absorbed by the green gases. We have green gases, namely carbon dioxide, methane, nitrous oxide, chlorofluorocarbon, and tropospheric ozone. These are the layers in our atmosphere which absorb radiation energy, and these are called greenhouse gases. This heats up the atmosphere, which in turn gives more energy to the earth, resulting in warmer surface. This increases the intensity of radiation from the surface. This cycle of process is repeated until no radiation is available for absorption. The net result due to these gases is heating up of Earth's surface and atmosphere. This is known as greenhouse effect. Without the greenhouse effect, the temperature of Earth would have been minus 18 degrees. So we are having more temperature varying from season to season. Otherwise, in the absence of the greenhouse effect, the temperature would have been minus 18 degrees Celsius. Concentration of greenhouse gases has enhanced due to human activities, making the earth warmer. According to an estimate, average temperature of the earth has increased by 0.3 to 0.6 degrees Celsius since the beginning of this century because of this enhancement. By the middle of next century, the Earth's global temperature may be 1 to 3 degrees Celsius higher than today. So the Earth becomes hotter and hotter. This global warming may cause problem for human life, plants and animal. Because of global warming, ice caps are melting. Sea level is rising and weather pattern is changing. Many coastal cities are at the risk of getting submerged because there is a increase in sea level. Sea level is rising. Therefore, the enhanced greenhouse effect may also result in expansion of desert. So, the coastal areas are getting submerged and the deserts are increasing all over the world. And efforts are being made to minimize the effect of global warming. Newton's law of cooling. This law helps us to calculate the amount of heat from a radiator to a room, or the loss of heat through the walls of a room, or cooling of a cup of tea on the table. First, let us state the law. Newton's law of cooling. The Newton's law of cooling states that the rate of loss of heat, represented mathematically as minus dq by dt of the body, is directly proportional to the difference in temperature delta T, where delta T is equal to T2 minus T1. T2 can be the temperature of the body and T1 is the temperature of the surroundings. The limitation of this law is that it holds good only for the small differences of temperature. The loss of heat by radiation depends on the nature of the surface of the body and the area of the exposed surface. Now we can rewrite the Newton's law of cooling as minus dq by dt is equal to small k into T2 minus T1. Here small k is the positive constant depending on the area and the nature of the surface of the body. Let it be equation 1. Suppose the body of mass m and specific heat capacity S, small s, is at temperature T2. And if T1 is the temperature of the surroundings, then the temperature falls by a small amount dT2 in time dt. Here d capital T2 and time is dt small t, and then the amount of heat is given by mass into specific heat capacity into change in temperature. Therefore, dq is equal to m into s into d of T2, capital T2. And therefore, the rate of loss of heat is given by, so dividing left hand side and right hand side by dt, that is the rate, time dq by dt is equal to ms into d of T2 by dt. That let it be equation 2. And now we can recollect the Wien's displacement law, that is the product of lambda m into t equals constant, and we also know from Stephen Boltzmann's law that the energy H is equal to E into sigma into t to the power of 4. Therefore, we can write equation 1 as minus S into d of T2 by dt equals k into T2 minus T1. That is substituting for dq by dt. Now we can rearrange this equation as retaining dt2 capital T2 and dividing and shifting this T2 minus T1 to the left side denominator equals minus of shifting the minus sign to the right hand side minus k divided by ms into dt. That can be written as minus of capital K into dt, because small k divided by m into s itself is a constant, where k is equal to small k by ms. Therefore, we can integrate equation 3, integral of left hand side, that is d of t2 divided by dt, t2 minus t1 is log, natural log or log to base e of T2 minus T1 equals minus of capital K into T. t. That is, integral of dt is t plus constant of integration is c. Let it be equation 4. Now we can rewrite the equation 4 in terms of exponential. So it becomes t2 minus t1 is equal to t1, if we keep it on the left side, equals e of minus kt plus c, again which becomes e of kt plus into e of c. So we can write the constant of integration and equation 4 as t2 is equal to t1 plus c dash into e to the power of minus kt, where c dash itself is equal to e to the power of c. Let it be equation 5. Equation 5 enables us to calculate the time of cooling of the body through particular range of temperature. That means if we know the values of T2 and T1, we can calculate the rate of cooling of the body through a particular range of temperature. Please note that this equation 5 is a valid approximation in the transfer of heat for a radiator or to a room, a loss of heat through the wall of a room, or cooling of a cup of tea. This can be determined experimentally although. That means we can verify the Newton's law of cooling through the experimental setup shown in the figure. Here, figure A, V is the vessel. V is a vessel, double-walled vessel containing water between two walls. This is containing water between two walls. A copper calorimeter C, capital C, contains hot water is placed inside the double-walled vessel. Two thermometers through the cork are used to note the temperatures T2 of water in the calorimeter and T1 of hot water in between the double walls respectively. Temperature of hot water in the calorimeter is noted after equal intervals of time, and a graph is plotted between log E T2 minus T1 for and small t time as shown in figure B. The nature of this graph is observed to be a straight line having a negative slope as shown in figure. And this proves the equation of Newton's law of cooling. Now we will answer some questions of worked examples as well as 1-mark questions. So question number 7 is a worked example. A pan filled with hot water cools from 94 degrees Celsius to 86 degrees Celsius in 2 minutes when the room temperature is at 20 degrees Celsius. How long will it take to cool from 71 to 69 degrees Celsius? Answer. The average temperature is 94 and 86. Therefore, it is average of these two is 90 degrees Celsius, which is 70 degrees Celsius above the room temperature. That is 70 plus 20 is 90. Therefore, under these conditions, the pan cools 8 degrees Celsius in 2 minutes. Therefore, using equation dt2 by T2 minus T1 equals minus of K into dt, we put the values change in temperature divided by time equals K into delta T. Delta T is the change in temperature. Therefore, change in temperature is 8 degrees Celsius divided by in 2 minutes. That is equal to K. Let it be K, and 70 degrees Celsius is the temperature difference above the room temperature. Let it be equation 1. The average of 69 and 71 is 50 degrees Celsius above the room temperature. So the change in temperature K is same for both the cases. Therefore, the change in temperature 2 degrees Celsius divided by time equals K into 50 degrees Celsius. Let it be equation 2. Dividing equation 1 by equation 2, we get 8 by 2 divided by equation 2 is 2 by time equals right hand side here is 70 degrees divided by 50 degrees, and K and K gets cancelled. Therefore, we can evaluate the time t or calculate time t as 0.7 minutes, that is equal to 42 seconds. That is the answer. Next we will answer 1 mark questions. State Wien's displacement law for black body radiation. According to Wien's displacement law, the product of lambda m into t equals constant, where lambda m is the maximum wavelength and T is the temperature in Kelvin or absolute temperature. The value of Wien's constant is 2.9 into 10 to the power of minus 3 meter Kelvin. State Stephen Boltzmann's law. According to Stephen's law, the radiant energy emitted by a perfectly black body per unit area per second, that is emissive power of black body, is directly proportional to the fourth power of absolute temperature. Next question. Name two physical changes that occur on heating a body. The two changes that occur are there is a volume change as well as there is change in electrical resistance. Question number 11. Distinguish between heat and temperature. Heat is the total energy of the motion of the molecules of a substance, whereas temperature refers to the measure of average energy of motions of molecules in a substance. Next question, will continue with 1 mark questions. Which thermometer is more sensitive, a mercury or a gas thermometer? Answer is gas thermometer is more sensitive as coefficient of expansion of gas is more than mercury. Next question. Metal disc has a hole in it. What happens to the size of the hole when disc is heated? Answer. When the disc is heated, the size of the hole increases. Next question. Name the substance that contracts on heating. Ice is a substance that contracts on heating. Next question. A gas is free to expand. What will be its specific heat? So it's the specific heat of gas is infinity when it is free to expand. Question number 16. What is the absorptive power of a black body? The absorptive power of a black body is E. 1. Sorry, E. E is 1. Question number 17. At what temperature does a body stop radiating? So at 0 Kelvin, the body stops radiating. Next question. If Kelvin temperature of an ideal black body is doubled, what will be the effect on the energy radiated by it? We know the temperature, the relationship, the energy radiated is given by the relationship H is proportional to T to the power of 4. Therefore, if we increase the temperature of the black body is doubled, H2 by H1 equals T2 by T1 into whole to the power of 4. When we increase the temperature, T2 becomes 2T. Therefore, it is 2T by T to the power of 4. T gets cancelled. It is 2 to the power of 4. 2 to the power of 4 is 16. Hence, H2 will be equal to 16 times H1. So, energy radiated will be 16 times. Next question. In which mode of heat transfer does the gravity not play any part? Answer. In conduction, conduction and radiation, the gravity does not play any part. Next question. Give a plot of Fahrenheit and Fahrenheit temperature versus Celsius temperature. Please refer the figure here. The x-axis is a Celsius temperature, that is degrees Celsius, and y-axis is degrees Fahrenheit, and the plot is shown in the figure here. So in Fahrenheit scale, the initial 0 is 32 and boiling point is 212, whereas in Celsius scale it is 0 and 100 degrees, that is melting point and boiling point of ice. Why birds are often seen to swell their feather in winter? When birds swell their feathers, they trap air in the feather. Air, being a poor conductor, prevents loss of heat and keeps the bird warm. Next question. A brass disc fits tightly in a hole in a steel plate. Should we heat or cool the system to loosen the disc from the hole? So you please note the disc is of brass and plate is made up of steel. So we have to find the answer for it. The temperature coefficient of linear expansion of brass is greater than that of steel. So on cooling, the disc shrinks to a greater extent than the hole. Hence the brass disc gets loosened. Now we will answer quickly 2 marks questions. Question number 23. If a drop of water falls on a very hot iron, it does not evaporate for a long time. Why? The answer is it is because of vapor, which is a poor conductor of heat and makes the water droplet to evaporate slowly. Question number 24. The earth without its atmosphere would be inhospitably cold. Why? It is because of greenhouse effect. The presence of atmosphere prevents the heat radiations received by the earth to go back. In the absence of atmosphere, radiation will go back at night, making the temperature very low and inhospitable. Next question. The coolant used in chemical or in a nuclear plant should have high specific heat. Why? It is because they absorb more heat with comparatively small change in temperature and extract large amount of heat. Yet a sphere, a cube and a disk made of same material are heated to same temperature 200 degrees centigrade. These bodies are kept at the same low temperature in the surrounding. Which of these will cool fastest and slowest? Explain. The rate of energy emission is directly proportional to the area of the surface for a given mass of material. Therefore, surface area of sphere is least. That is, sphere has a least surface area, whereas disk has a large surface area. Therefore, cooling of disk is fastest and sphere is slowest. Next question. Why a pendulum clock generally go faster in winter and slow in summer? Part B is why the brake drums of a car are heated when it moves down a hill at constant speed. Part A is the time period of pendulum is given by the relation capital T. It is T equals 2 pi into square root of L by G. In winter, L is shorter, so its time period reduces. And in summer, L increases, resulting in increase in time period. So the clock goes slower. Part B. When the car moves down the hill, the decrease in gravitational potential energy is converted into work against the force of friction between brake shoe and the drum, which appears as a heat. Next question. The plots of intensity versus wavelength for three black bodies at temperature T1, T2 and T3 respectively are shown. Arrange the temperature in decreasing order. Justify your answer. The figure is shown here. So lambda on x-axis, T1, this is T2 and this is T3. So we have to arrange it. According to Wien's displacement law, lambda m into T equal to capital T equals constant. Therefore, lambda 1 is lesser than lambda 3 here and lesser than lambda 2 here. Lambda 2 is highest. Therefore, T2 is T1 is greater than T1 is greater than T3 greater than T2. Next question. The triple point of water is a standard fixed point in modern thermometry. Why? The melting point of ice or boiling point of water not used as standard fixed points. We have to give the reason. Answer. The melting point of ice as well as the boiling point of water changes with change in pressure. The presence of impurities also change the melting and boiling points. However, triple point of water has a unique temperature and is independent of external factors. It is that temperature at which water, ice and water vapor coexist. That is at 273.16 Kelvin and pressure of 0.46 of mercury. Next part will be, we will take up chapter number 12, that is thermodynamics part 1, wherein we will study about thermal equilibrium, zeroth law of thermodynamics, heat, internal energy and work. Till then, goodbye.